Okay, I'm Muqsit Azeem, and I will be talking about our paper 123 Go, Policy Synthesis for Parameterized Markov Decision Process via Decision Tree Learning and Generalization. This is a joint work with my collaborators from Germany, Czech, Iran, and Austria. I know that the title is quite long, so there are 4 things. We'll go into these things one by one. So there is a policy synthesis, parameterized MDP, and decision tree learning and generalization. So let's first see why do we care about MDPs. So cyber physical systems are everywhere, and this was well motivated yesterday. And the thing is that in cyber physical systems, agents make decisions, and when these decisions are made, then there is some probability of failure and success, right? And so essentially there is sequential decision making that is involved, and you have uncertainty. And MDPs are the nice model to represent these things. So let's see, using an example, what MDP is. Right, so in MDP, you have some states. Here there are some special states, for instance, initial state, goal state, bad state. And so there are some states, and in each state you can take some action. So for instance, in initial state, there are few actions A and B available, and the agents can choose to pick either playing A or B. There are some probabilistic transitions that are available because the uncertainty is involved. So in state S, the agent can choose to play A, and then with 30% probability go to goal state. With 40% probability can stay in the same state, and with the rest it goes to the bad state. Right? And what we are interested in is finding a policy. And what a policy is that in given a state, what action I should play. So essentially, it's a function from state to action. And what we would like to do is to find an optimal policy which optimizes some objective. And in this paper, what we are doing is we are focusing on reachability objective. Essentially, we want to find a policy sigma which optimizes the probability of reaching the goal state. So diamond goal is reaching the set of goal states if we start from the initial state. And because this is an optimization problem, this is hard to achieve. So what people have done so far is they'll look for near optimal policies. These are simpler than finding an optimal policy. And in this paper, we are focusing on arbitrarily large systems. So here, for instance, there is an example where initial state is denoted as init, and there are 2 actions that you can play, up and down. Right? If you go up, then you go to some cloud of states, which could be like millions or billions of states. And if you go down, then you go to T with 99% probability. And if you take action C from T, then you go to goal. Right? And if the probability, if you ask this question that, okay, I'm fine with near optimal policy, and I want to optimize the policy of reaching the goal state, then taking down and then taking C would be good enough for you, and you don't really need to analyze the whole billions of states in the cloud. Right? So there are techniques which try to deal with large systems. For instance, there is storm model checker. There are some statistical model checker that try to solve this technique. But as you increase the size of the models, then they fail to give nice policy for this. So for instance, either this entire model does not fit into the memory, or they give some policy which is bad.